Hello everyone, welcome to CEDA Lighthouse Project Season 2, the power of graph convolution networks, master graph-based machine learning. Myself, your host, Roopesh Bharatwaj K R. Well, today is our final session, so we are in week 5 and class 10. So today we're gonna discuss about the entire recap right from like a 1 to 9 sessions and followed by a question and answer session. Let's jump into our today's session of complete recap right from graph data, graph neural networks. So graph data, the term graph data is basically like graph structured format data. So which is basically is a collection of nodes and edges. So graph data is used for like complex relationship and it's used for connecting like different entities. And there are like many examples which we can connect to our real world applications where graph data can be used. One example is like our Google Maps, so which contains transportation networks and like our one important example, like social networks where graph data is being used, say for example, Meta or Threads or Twitter. So these are like a basic examples where the graph data can be used and much more, even for example, like recommendation systems, building, or a basic application also we can use the graph data. That's the basic applications where the graph data can be used. So there are two different types of graph data. They are digraphs or also called directed graphs, and another known as called like an undirected graph. So what is a directed graph and undirected graph is like directed graph which have a direction. That means like pointing from one node to another node directly. It has like a direction in it, or also it can have like a reverse direction as well. Unlike undirected graph, which does not even have like any directions. Say for example, in our graph, which we can see is like node one is connected to node two. So we are not sure like how the direction of the graph is being connected. Either it can be both from one to two or two to one. So that's the basic difference between like a directed graph and undirected graph. So one of the biggest examples of graph data is like a Facebook, which we can say, and in our example, which we can see in a Facebook graph. So here, the nodes are the people, and their relationships are the edges. So that's called either can be like a friend, wife, or any other relationships we can have it. So each and every person's here is like a node. For example, Ram's wife is Sita. So here the wife is a edge and Ram and Sita is a node here. So unlike we have like a couple more examples where like a movie graph. Here the each and every person is a node, and then the movie name, it's like object or entity, that is also a node. And the way it is connected, say for example, the Tom acted in movie Journey. So Tom is a node and Journey is a node. So acted in is a relationship, and Journey is being directed by Tom Cruise. Here, the directed is an edge, and it's our relationship. And Tom Cruise, he's a person. He's like obviously he'll be a node. So likewise, we can connect many real world applications by creating like a nodes and edge relationship, and we can traverse in any direction when if it is has like a directed graph. So here you can see is like a the chemical reaction, so where it is like completely undirected graph here. Say for example, carbon atoms contain covalent bonds, the covalent bond of hydrogen atoms. And hydrogen atoms contains a relationship of like hydrogen bond, and hydrogen bond atoms contains a node of like oxygen atoms in it. So this is a basic undirected graph for chemical reactions. So same like here. We have it's a combination of the both directed and undirected graph. So here is like a example of like a directions from one place to another place. Here like a Times Square, New York to New Jersey. So that's a node. Here the relationship is like a distance. So distance is like a 10 miles exactly from Times Square to New Jersey. So unlike another option we have is Times Square to Boston. So here the relationship we have like a miles per hour. That's 150. So that is not fixed. So we are not sure like what it miles per hour it can be like in either of the directions. So that's why here we have like an undirected graph here. So the distance wise is like 250 miles, but it's in a directed graph we have. So likewise, we can have like any combination of like directed or undirected graph. So that's the basic example of a graph data. So we all know like what's a graph data and graph database. So graph database is uses like graph structure to represent and store the data. So basically all we know is like graph data, it contains like nodes and edges. And unlike the same, the graph database also contains the same. Why? Because that's a database to store each and everything. Like for example, Neptune in Amazon, or like a Cosmo DB in like Azure, or like Arango DB, or like a Neo4j. So these are like a different APIs which we can use for like graph database, or we can consume the graph database directly. So one of the major advantage of graph database is like complex relationships. So it can understand complex relationship in like in a different way of connections we can understand. And the advantage is like a natural representation of real world scenarios. We can like come up with like any different sort of ideas which can be utilized in real world situations. Like either like a friend is connected with another person, or like even for like basic household applications of like Alexa, we can use a graph database, and that's the power of it. And next important like advantage is like efficient representation of relationships. So here we can understand easily how the way we represent each and every node and the edges as well. And in the biggest advantage of graph database is like it can traverse in any direction, from the top node to the like a bottom node. It can traverse, and it can utilize the complex queries. Basically, like in graph database, like in Neo4j, we use like Cipher queries. So Cipher queries, its base is like a structured query language. That's the basic of like a Cipher query language. So once we have like a clear-cut idea of like what's the SQL and everything, so Cipher query will be like much more easier and everything. And the biggest advantage of like graph database is like it's flexible schema. So we can manage our own schema, and we can develop our own schema here, and it's not defined to a specific set of schemas. Why? Because like we have like n number of nodes and edges, so it's up to us to decide how the schema looks like and how can we customize the schema. So we as we talk about like advantages, but still it has like disadvantages as well of graph database. So one of the biggest disadvantage of graph database is like storage. So it contains n number of nodes and edges. So it is very complex to store this database. And because of the complexness in storing a database, it becomes very expensive for like the graph database organization to maintain those datas and retrieve them. And also it leads to like complex in data modeling structures. So we can't based on the number of queries, we should like a data model it. Since it has like a large number of queries, we have to customize that, and we need to like curtain in a proper way. Otherwise it leads to like expensive, and storage is also expensive, and like read and write operations also very expensive based on number of nodes and edges. And the another different example is like it is learning curve right now. Why? Because the graph database is currently in like uh, in a research and development. It's being used by multiple places, but still we are in a place where we need to develop like a much more in terms of graph databases. So now let's jump into like several applications of a graph database. So one of the different applications of graph database we can tell is like social networking and recommendation system, we can say fraud detections, we can say semantics analysis, we can say like telecom networks, urban planning, supply chain management, road networks, biological networks, and knowledge graph. So these are the domains where we can utilize the graph-based databases, and it's not limited to this situation as well. Why? Because it's completely applicable to like real world applications or real world situations. So let's start about like a graph neural network and its history. So the graph neural network all started from right from like in 1940s. That's the basic artificial neural network has been like discovered. And later on, like we started to emerge in late 2000 for specific neural network on like graph structure data. And later on in 2019, the graph neural network model was first ever discovered, and then it got implemented and it got extended in 2016 using like graph encoders. And further on, the GCN has been like published in 2017, and based on the GCN, and furthermore, the Graph Attention Network has been published in 2018, and later on, based on Graph Attention Network, subsequently, Recurrent Neural Networks has been published. Since like recurrent neural network and long-term short-term memory networks share the same, so in 2018, again, a paper titled Graph Convolution LSTM network has been published. And then later on, since we all evolved in using like a transformer architecture, the graph transformer architecture has been evolved. So these are like a different years of neural networks which we see. So what is the basic of neural networks? So basic neural network is contains layers of input and like multiple hidden layers, and finally we have like a output layer. So let's kind of think of like a human brain, how it works. So once we start to speak, we will be conversing in like in our linguistic based on our ability, and in our brain there's like a lot of processes being carried over, so lots of signals is being converted, like multiple million signals are being like transferred if we want to speak or do some small set of actions. Similarly, in a neural network, the same set of actions is being performed. Given a user inputs a data, and the different based on the number of the data and everything, the several computation is being processed inside the hidden layers based on architecture. And finally, we are getting an output layer, say either is for classification, prediction, or whatsoever the given task. So as I said earlier, the hidden layer, which contains basically these are like three different layers, like input layer, hidden layer, and output layer. So input layer is like where we'll be giving our input, and hidden layer where that's like a lot of computation is being processed inside. Say for example, like a feed forward pass and back propagation is being computed inside our hidden layers, and finally using an activation layer and everything, we are getting the output layers. So one of the biggest applications of like a neural network are the image processing, computer vision, chat gpt, or architectures based on like transformers, and LSTM networks, we can say, and inception networks, and ResNet. These are one of the biggest neural network architectures right now in our market. So basically, like a graph neural network. So we are aware like what's the basic of neural network. The basic neural network where the input will be of relational type, like CSVs or anything like that. But in a graph-based neural network, the input is completely graph structured data, and it is used for many mathematical computations internally. And finally, we'll be getting different interactions between which node we did and which edges, and it's completely used for like complex tasks like recommendation system, social network analysis, and molecular structure analysis, or like chemical structure analysis. So basically, in a graph neural network, there are like a different formats and different structures and stages are there. So first input is like a graph structure data, and then is like a message passing scheme. And further to the message passing scheme, like we'll be representing the nodes based on the characteristics and their attributes. And then we'll be obtaining information of edge level information with like information associated with the edges and everything. And then we'll be doing like aggregation function. So aggregation function where we'll be finding the neighbors, the whoever is connected with the nodes and everything, and we'll be combining the information of the each and nodes and everything, and then we'll be doing like a summarization of summation of the different nodes and the information of the edges, and then we update the node function once the aggregation is done, and finally we'll be doing a prediction. The prediction can be like either node labels or node links or generated graphs and subgraphs. So this is a basic example of what's aggregation of aggregation works like. Say for example, the target node is 4. Now in a graph, we can say the target node 4, we can see like which are the elements are directly connected with 4. So 3 is directly connected with 4, and 5 is directly connected with 4, and 6 is directly connected with 4. So that's what we have explained here. So that's like a basic, like first layer of aggregation. Now let's consider 3. So in this three, one is directly connected with three, and two is directly connected with three, and four is directly connected with three. So this is like subgraph level information aggregation. So once this subgraph level of aggregation is considered and all this information are passed into three. So now all the information of three is aggregated and passed into four. That's how each and every node and neighbors are being connected. And that's how we will be finding an aggregation function. So this is a basic explanation of what's aggregation function. So we'll be considering each and every node in a graph, and then we will be finding like a transformation feature vectors based on like a node's neighborhood, and then we'll be computing the weights of each neighborhood using a softmax function. Further to that, aggregated feature vector then passed through a activation function. Either it can be like a relu or leaky relu, or whichever is the activation function we are using. And then the resulting feature vector becomes the output of the graph convolution network. How we got, for example, in our last slide, we got like three. And further to each and every information, the further aggregation is being computed. And this is processed multiple times in each layer, each node feature, weights are being updated. And finally, we are getting a final like aggregated function, which enables us to predict. So this is like a basic example of what's like a graph neural network versus a neural network. So data is in graph neural network is like graph structure data, unlike in traditional is like a grid or sequential data. So input contains graph with nodes and edges, but in a traditional it contains like matrices or a vectors. So output, we in graph neural network, we can have like a whole graph or like a independent graph. But in traditional neural network, it is completely dependent on either it's going to be like a prediction task or a classification task. And next is like the aggregation function. The aggregation function in graph neural network is like a message passing scheme. But in traditional network, it's like a forward processing. And there are like different applications which we can do using graph neural networks. So it's like called like a social network we can do, recommendation systems we can do, biological networks we can do. Unlike in our traditional applications like image processing, speech recognition, NLP, or object detection we can do. The computation complexity. Here, the computation complexity of graph neural network is completely based on graph structured data and its connected patterns. Unlike in traditional neural network, it is completely based on input size often data. Either it can be like it can be like a structured format, can be, or like in like MB size, it can be, or like a GB size also it can be. So advantages of graph neural network. So graph neural network basically they are like effective for graph structure data. And like next important advantages of like GCN, we can say is like it is used for like a parameter sharing across different nodes. Different nodes we can share it. And next is like a hierarchical learning capability it has. And the advantage of one of the biggest advantages it has like efficient handling of irregular data. The similarly it has like several disadvantages as well. So if there's like a unseen graphs in the data, that is like a biggest disadvantage. Why? Because there's no node connected within a data. That's a different thing. And computation complexity, it has like then based on the size of the graph, it's that much complex of a neural network architecture to predict and everything. And it is like completely sensitive to the graph structure. So we can't include like any like tabular formats or anything. That's the biggest thing with GCN. So they are like a different types of GCN currently in our market. They are like graph autoencoders, graph recurrent neural networks, graph transformer networks, graph attention networks, and graph convolutional LSTM networks. So each and everything has their own pros and cons. Is the graph autoencoders are used for like anomaly detections and network visualizations. Like a graph convolution networks. So basically, it aggregates the user information. So it is also used for like node classification, link prediction, community detection, and recommendation systems. And we have like graph attention network. So it used for like a recommender system building, graph classifications. So graph recurrent neural networks and graph convolutional LSTM networks, they share the same, and they are used for like community detections, link prediction, node classification, and graph generation. And finally, the graph transformer architecture. So graph transformer architecture uses like architecture of like a transformer, and it is used for different several tasks, like from like an image task or NLP task or a speech task. It also used for it. So there are like several applications of graph machine learning applications. So basically, the graph-based machine learnings are divided into four major categories. They are like graph level predictions, node level predictions, edge level predictions, and sub-graph level predictions. So each and everything has their own set of predicting capabilities, like from like recommendation system building, the customer clustering alignments is there, network analysis is there, graph classifications is there, image processing is there, supply chain management, fraud detection, community detection, and node classification. So each and everything will be like mostly the applications will be sharing, and the level of the prediction is based on the graph level or node level or edge level or subgraph level. That's the catch here. So let's jump in like a proper like popular graph visualization tools currently in our market. So one of the biggest tool is like in Neo4j Bloom, which we have, and Network X library generally we have used, and like Cytoscape is there, Deep Graph library is there, iGraph is there, D3JS is there, and PyGeometry is there. These are like a major visualization tools available in the market for graph-based data. So let's talk to like what's the difference between like a native versus non-native graph DBMS. So the native versus non-native. So what is non-native? Non-native is basically like it's a relation database where it contains like a MongoDB, Cloud Firestore, or like Cassandra. It has, but in graph-based, that's native. It is completely based on graph structured format of data. So we all aware like Neo4j is there, Amazon Neptune is there, ArangoDB is there, and Cosmos DB is there. So basically, like a native versus non-native. So in non-native, there's like two types of databases there. One is like a database management system is there, and relation database management is there. That's the complete difference between native versus non-native. So what's like a non-native? So when we compare with non-native with native based on the graphs, the structures and like of a database management system. So in non-native, it is like completely slow performance with large or more data connected in it. In native graph, it's like very highly effective for traversing complex interconnected data. And also it performs well for large and connected data sets. And in non-native one, we there is a like concept called persistence layer. So it's completely dependent on the persistence layer in non-native graph databases. For example, Cassandra and MySQL. But in native graph, say for Neo4j or Cassandra, like some other like DB or anything, the graph-based structure automatically it has like inbuilt. Basically, it has like inbuiltly it has like persistence layer. So since it has like persistence layer, it can handle the graph-based structure very easily. That's the difference between the native and non-native. Since like it has like our non-native does not have like a persistence layer, and it has only like in several only a couple of applications like Cassandra and SQL, and it may struggle with performance as data becomes more connected or larger. But in native, it scales very good and like a very accurately for graph data sets for a larger scale of data. And in non-native, it's completely like it's not useful for like graph-based operation. And for graph, using like a native, it's completely used for like a traversal and pattern matching. So in non-native graph databases, it requires like a small or less connected data sets for like for in order to do like a very like a good task and everything, and it does not require like a low latency. For a graph-based dataset, it's used for like critical applications with large and interconnected dataset. For example, like fraud detection or like recommendation system management. It requires a more of less interconnected datasets in it. That's the one of the like a difference between native and non-native one. And in non-native one, it is facing a lot of challenges in like in based on the size and everything, because like each and every read and write operations in like a non-native graph database MS, it requires lot of memory to consume and a lot of RAM it consumes and a lot of cost is there. But in like a native one, it's like future proof, and it becomes irrespective of the size of the data. In graph database, we can connect n number of nodes and edges. That's the biggest advantages. And it is like kind of future proof as well. Suddenly we have like connection of like 1 million users within a day or so. It can easily scale up. That's the biggest advantage using a native graph and non-native graph. The next important thing we can say is like non-native persistence layer. So each and every development team can leverage existing knowledge of non-native persistence layer, but in native, it requires like a familiar. That is the only thing. So why? Because the graph is completely a new database technology, and it requires a lot of familiarization for that to work with it. And if there's like not that much of like a familiar for working with graph database, then it becomes like a very difficult to work on it, because based on like persistence layer and everything. That's the biggest thing. So next, let's jump. What is difference? What is then RDBMS versus Neo4j, how it's being done. So let's try to solve an example sum. So here we have like a basic table, so which contains ID of like three IDs it has, and the column called like group name, it contains like top group, some group, and other group, and it has like a foreign key of parent ID 112. So now we have like a question: what is the parent ID of the group with an ID of 3 in the group table? So we got to find what is the parent ID of group with ID of primary key ID of 3, and what is its group table ID. So let's see how it's being done. So for that, in SQL, we need to do like a three different, so like a where conditions we need to put. So how it is being done in a bottom to top approach. So consider is like a bottom to top approach from groups where ID equal to 3 that we'll be finding. And again, from groups where ID equal to select ID, select parent ID based on parent ID. And finally, where ID equal to select parent ID from groups. So each and every cycle, it is like computing from top to bottom to top approach. So once we do that, we will be coming to a solution called like one. So here what is happening is like we are locating the innermost clause, and then we are building the query plan for each sub queries. And then finally, we are going into the innermost clause, and again, we are repeating the steps, building the query plan and locating the innermost query. And finally, we are getting the answer as one. So now what is happening here? That means like here we are doing like three planning cycles, and three index lookup and three DB read and write operations. So why? Because three in the sense like look about a where condition here. So where ID equal to 3 is the one, and where ID equal to select parent ID, and where ID equal to select parent ID. That's three times. So that's like called like a three times reading operations is there, three times index lookup is there. So since for one operation we are doing like three different cycles, read operations. So completely it's like a complex task, and it requires a lot of memory basically. And in basically in databases, each read and write operations is expensive completely. Since we have like three read and write operations here, it is basically expensive as well, and it takes like a lot of time, and it also takes a lot of memory. So since it is taking like a lot of memory, so we can say like it's like a O of log n, and a lot of time as well. It's like a logarithmic time complexity, we can say. So let's consider the same example using Neo4j. So in Neo4j, basically we need to find what is the parent ID of a primary key with ID with 3, and whose ID is 1. So let's see how we gonna find the ID. So this is the basic third ID, and third ID is directly connected with the edge of like 6, and 6 is connected with ID of 2, and 2 is connected with ID of 5, and 5 is connected with ID of 4, and 4 is again connected with ID of 1. So basically, why we are using the pointers is like it is like index-free adjacency. In Neo4j, like each nodes and edges, they are linked via pointers. That is the one of the basic example I can use like our linked list in our data structures. That is also connected using a pointers from one node to another node. So let's see from a group ID of 3. Now the group ID of 3, it's directly links with 6. Okay. So now again the 6, it's going to see where the 6 is connected. So the 6 is connected to the group ID of 2. So in group ID of 2, which links 5 and 6. 6 we have already visited and 5 is the only thing remaining we have. So directly it jump into the child of 5. So now in child of 5, it links two things. Two nodes it connects, 2 and 1. So now we're going to first visit 2. So 5 and 6, we already visited. That means there's nothing to visit. Again, the left one is like 1. So we're going to visit 1. In 1, there's 2 more nodes, subnode is connected. That is 4 and 5. So let's jump into the node number 4. Why? Because 5 is the one we visited previously. So now let's jump into node number 4. So node number 4 links 1 and 1. So let's jump into 1 and 1. So that's the only thing left over, the 1. That's what we have predicted with parent ID equal to 1. So here we have used like only single line query. Since the single line cipher query, it does not even takes like SQL like 3 read and write operations, 3 cycles or anything. And the time complexity is very simple compared to our SQL, which has like logarithmic time O of n. And here we are using constant time here. That is O of 1. So it is like, it looks like few index lookup it takes, no table scans, and it also like reduced duplication of the data here. That's the biggest advantage of Neo4j or like graph databases we can tell. So how well it works compared with relation database structure. So why our Neo4j is like very fast compared with our like a relation database system? Because it contains index-free adjacency. So the index-free adjacency is like a basic key behind that. So it is responsible for lightning fast retrieval of data and relationship via pointer. So that is the important thing here, concept here. So let's talk about what is Neo4j. So Neo4j is like a graph database and it contains like lot of operations and like lot of sub operations in it. So one of the biggest operations in it is called like graph data science library. So graph data science library is used for graph analytics and everything. And one is like Aura DB. So since unlike we already know like what is like Neo4j browser, that's like a basic desktop version. Aura DB is like a complete online version is there. And next important thing is like visualization tool. So Neo4j Bloom is like a biggest visualization tool which uses and the standalone like a cipher query language for graph for Neo4j. That is the important thing we're gonna discuss. So let's jump into like a basics for fundamental queries. So here is an example like of a query. So which matches a person with the name of Dan and his relationship is loves, whom is another node connected with the variable. And finally, it returns that person whom he loves or like who whatsoever the relationship. So this is a basic cipher query language. And the cipher query language uses SQL as a background for it. And like if you're like a clear much more like pretty in terms of SQL, the cipher query language will be much more easier. So let's see like how a node can be connected with like using like cipher query language. So let's create a person. The person is a variable and we need to give a label for the person. And inside a label, we're going to give a node properties. Either it can be like a name, age, or anything. That's the basic of like how to create a node. So similarly, or how we can create a relationship is like we have to create like another than same node. We have to create a node, two different nodes, and we need to connect it with a relationship called Y for edges or anything like that. So how it is being connected is like Now we'll be creating basically a person one, and he is directly connected with the person two in terms of the different relationships. It can be like friend or wife or anything. This is how it's being connected. And also we can give like a edge properties. So since we know like Aaron's wife is Mary, and now we can say like like a property in terms of like since when. That's the biggest property. The time background we can give, or like when it happened, how it happened, etc. Like that also we can give it. So let's talk about the graph data science library. So graph data science library, which contains a lot of algorithm which is being run internally, used for graph ML applications, graph neural network applications, link prediction and applications and everything. And also it has like a inbuilt production support for like a for basic sophistications and for like end-to-end operations as well. So the graph data science is a mix of graph algorithm, graph visualization, graph analytics, graph query language, data exploration, and feature engineering. It's it's a intersection of all these elements. So let's talk about like a link prediction. So basically, a link prediction is a way of predicting which node is going to connected with another node, subnodes, and who or whom is being connected to the next. That is the biggest advantage of link prediction. So here we can see in this example, the dotted lines. So the dotted lines here is like a future prediction. Say how it's being predicted futurely based on the shared neighborhoods it's being predicted, and the same properties, same relationship, same edge relationships and everything. So let's talk about what is a topological link prediction. So basically, the topological link prediction is used to determine which node is being close to another node, and then based on that, it computes a score, and that enables us to predict a new relationship between them. This is the basic of a topological link prediction. So in our graph neural network, in Neo4j, we have like couple of inbuilt library for our topological link prediction. So in topological link prediction, like there are like several advantages, which includes like no need for additional data in it, and it's like computationally effective, and it's robust to noise and missing data. So these are like a basic advantages of topological link prediction. So let's jump into our different prediction algorithms, which is being inbuilt in our Neo4j. So their basic algorithms are like ADAR admic, common neighbors, preferential attachment, resource allocation, same community, and total neighbor. So basically, the purpose of all these algorithms are only one, which is used to measure the closeness of each nodes and the shared neighbors. So in that's for like other admic as well. And for common neighbors, so let's think of a situation like two different strangers are there who have a friend in common are more likely to be introduced than who don't have friends in common. That's the way of approach using common neighbors. So the preferential attachment. So we all aware like we did a task of like a topological link prediction based on like Aaron Mary love story, and we found that like preferential attachment gives us very high score. That means like they are very well connected with each other based on our different use cases and everything. But basically, what is the internally happening is like it finds the closeness based on a node and their shared neighbors. So, and this is the same for each and every algorithm, the basic objective, but internal computation, it is completely like different from each and every algorithms which we use, right from like total neighbors or community detections and everything. So finally, let's jump into like what's the recommendation system. So recommendation system is a technology that used to like suggest either like a product or a services or contents to the users based on their preferences or different patterns of their behavior or like a previous historical purchases or the entire session based informations which we can be giving a recommendation system as a whole application to our users. That's the basic of a recommendation system. And there are several different types of recommendation systems being used currently. So they are like collaborative filtering, content-based filtering, hybrid systems, context aware recommendation system, session based recommendation systems, matrix factorization machines, temporal and sequential models, and reinforcement models. So here let's talk about like different use cases which can be applied in graph neural networks. The collaborative filtering, content-based filtering, hybrid systems, context-aware systems, and session-based systems can be used for graph neural network applications. Why? Because they contain each and every informations of like a pre and like their past historical one, or based on the content which they use, or based on the context, the environment, or the session of the current like web page or anything that can be used for modeling GCN, and finally use that model for a recommendation of an applications or a product or anything. So let's talk about the recommendation system in detail. Now let's talk about like collaborative filtering. So collaborative filtering is basically it contains two different things. One is like a user-based filtering and item-based filtering. So once we want to talk about like what's user-based filtering and item-based filtering, so one of the biggest example I can give is like which item or like which user and his preferences, or which item is being considered by the user, we can say. So let's go in bit detail about it. So let's talk about a user. So the user-based collaborative filtering. So this method here we which identify the users with similar behavior or preferences, and it recommends that user who have liked or also interacted with it. So here Aaron likes t-shirt, jeans, and cap, and his wife likes t-shirt, jeans, cap, and shoes. Now automatically Aaron may also like shoes. Why? Because his wife likes. So this is the one like one example let's consider. Here the relationship is like a wife here, and it can be of friends or friends of friends or anything. Why? Because one person likes and other person may also tend to like the same item. That's the basic concept of user-based filtering. So another one is called like item-based filtering. So here the item-based filtering, instead of focusing on similar users, so this approach looks at similarity between different items. So for example, if a user has a like or interacted with a particular item, other than that or similar, it may also be recommended. Say for example, Aaron likes t-shirt and Mary also likes t-shirt. So the t-shirt, like many people who shown like interest in t-shirt, they also shown interest in hoodie as well. Here, many people may dislike hoodie and many people may like hoodie. But for Aaron, since he liked the t-shirt, he may also like the hoodie as well. That's the basic concept of item-based filtering. So this collaborator filtering has like a major problem that's called like a cold start problem. The cold start problem refers to the challenge that arises when a recommendation system encounters a new users or item for which it has like a no historical data. In these cases, the system may struggle to provide accurate and relevant informations. And since it does not have like a lot of prehistorical or like a transaction data, it may lack of information about the preferences and behaviors of the new users. That is the biggest problem using cold start. So next is like there are two types of cold start problems is there. So one is like a new user cold start problem and new item cold start problem. So new user cold start problem. So when a new user joins a platform or like a services. So here there will be like no previous interaction of the data. And as a result of that, it is difficult for like personalization of recommendation system to that user. So a new item cold start problem is like when a new item is being introduced in the market or a system, so which has like typically no historical data in it, and which makes the user interactions with that item. This makes challenging for that product or item to be like having recommend to another user. That is one of the like a new item cold start problem. So basically, how can we overcome this like a problem with collaborative filtering of new user cold start or new OSM cold start? So the best answer for that is like the content-based recommendation system or like a hybrid approaches or contextual information. These are like different types of recommendation system as well. We're gonna talk about it. So let's talk about what is a content-based filtering. So the content-based filtering is also a type of recommendation system that able to give us each user a very personalized item of recommendation system. So it can be like different approaches, and it matches the each and every person based on his interest and taste. So let's talk about Aaron. So Aaron likes to watch Marvel movies. Then uh, he also likes to watch we can say like Aaron likes Marvel movies. So that is being watched by user. So now he's automatically considered by that system to watch Batman movie. Why? Because these are all comes under like the same umbrella. That's called like content-based filtering. So they are like similar movies. For example, if he watches like action movies or like some other movies, he'll be recommended with like similar types of action movies or similar types of genre or similar types of music of his interest or similar types of products or anything. So why the content-based filtering is better? So one is like no need for like different people data, no other third parties data is not required. So and all of the data is completely and solely based on your preference, your patterns, and your behavior. That is the biggest advantage of content-based filtering. So let's talk about hybrid system. So hybrid system is like a combination of both collaborative filtering and content-based filtering is called hybrid systems. So how will like hybrid system can have an edge over other systems? So one of the biggest is like improved like accuracy in it. We can tell that's the biggest thing compared with our content based and like collaborator based. And next important thing is it mitigates the cold start problem. So no user information, no prehistorical information is required, and it directly mitigated using hybrid systems. And then it is used for like a diverse and like a different set of recommendation system. It can be used, and it is used for like a sparse data, and it's completely robust for that. And here in the hybrid system is completely based on user preferences and his patterns and everything. And it's also used for like flexibility and customization. And more all, it is like enhances the like engagement, and basically it reduces like a biasness of each and every model. And that's how the hybrid system is like has a much edge over other systems. And it is used for like a dynamic environments. It can be used for like applications with like a product recommendation system, or like a music recommendation system, or like movie recommendation system, or etc. And it completely like customizable based on our business objective. There are like few examples of hybrid system, or like e-commerce platform like Amazon is being used, streaming service like Netflix is being used, and music like Apple Music or iMusic is used for like our news content generation or content creation. Recommendation system is being used. Social media platforms like Facebook or like Threads is being used. Then like travel accommodations sites like Travel Guru or like some other applications is being used currently using hybrid system. So let's talk about what's a context aware recommendation system. So context aware recommendation system, which uses like a graph based application. So where the user interactions or individual items are being much more observed here, and then it's being considered, and next it's converted into graph structured format, and then later on it's being processed used using our like nearest neighbor algorithm, and then it's sent to our recommendation system. So basically it enhances the personalization, and it improves like the relevanceness and timeless of it. And it also mitigates the cold start problem, and it is for like a diverse recommendation system applications, and it is used for like dynamic environments, different environments it can be used, and it is can be customized for like specific set of goals. And basically in like hybrid system like are used for like e-commerce retailers, travel hospitality, health and fitness, and also used for like a news creation platforms, social media platforms, and healthcare platforms. And finally, it's being used for like our Google Maps and navigation services as well. So let's talk about like a bit more about. If you have like any questions, you can raise me anything in meantime. Guys, do you have like any questions in between? So let's talk about like what is matrix factorization. So matrix factorization is also like a type of recommendation system which is used to model user item interactions and make personalized recommendation system. The core idea behind a matrix factorization is to represent user and items in a lower dimension latent space and to capture hidden patterns and preference in it. So they are like different basics of like a matrix factorization. They are like user item matrix, latent factors, matrix reconstruction, learning latent factors. So let's take example of like a movie, like five different movies is there and five different users is there. How the each and every user rates the five different movies. That's the basic concept here. So let's consider like a rating of like a movie number four. So we have a table representing the rating of five users for five movies, and let's create. We have created a sparse matrix since not every user rates every movie since and the rating ranges from 1 to 5 here. So let's consider the movie number 3 where user 4 has given rating of 2 and the movie 5 also he has given a rating of 2. That means like both the movies contains like similar patterns or like similar his likeliness is there. That's why he has given ratings for that as the same type. So what is a sparse matrix handling? So we will be filling the missing value or like null ratings with zeros in order to compute the complexity. And latent feature discovery is like providing a more compact and information representation of the original data. So here we'll be using a collaborative filtering, which used to discover latent factors to find users who ratings aligns closely with users. So the user 4 has given a rating of like 2 for movie 3 and 2 for movie 5. So let's see his the closeness of another users compared with the his that user. So the most closely related is like we can say like user 5, user 3, and user 2. That's how it's very well closely connected, and collaborative filtering is being used here. So basically how the evaluation is done is using like both parameters here, the root mean square error and mean square error. So how well it is compared to our previous architectures of recommendation system. So it combines both collaborative filtering and matrix factorization. That's the biggest advantage of matrix factorization. So let's talk about LLMs. So LLMs are like large language models, which is currently used all are aware of that. So examples like Llama is there, Pama is there, ChatGPT is there, and OpenAI is like different like GPT-2 versions is there and everything. So basically, in our current market, the chat GPT is being trained using like 175 billion parameter. That's like chat GPT, like 3.5 and 3. And chat GPT 4 is being trained with 1 trillion parameters. And Pama is like, it's again, is being trained using 540 billion parameters. And like a Meta's 175 billion parameter is there. And BERT is there. And like Roberto is there, and a couple more like LLMs are being used in the market. So how fine tuning is done for a LLM? So first of all, basically we'll be choosing the pre-trained model, and after the choosing that, we'll be doing like a different set of like preparations for data preparation is there, and task identification is there, and then we'll be doing a tokenization step, and then we'll be doing like a model, like refining the model architecture by like updating the last layer, or like fine tuning the last layer, and pre-training like and training based on that. And finally we have like a training and evaluation using our accuracy and matrices. That's the basic concept of like our fine tuning of LLMs. Let's jump into LangChain. So LangChain is like so basically it's a framework used for developing like a large language model applications. So there are like a couple of features for like LangChain. So they are basically is like one important thing is like chaining concept is there, and next is like context awareness is there, and reasoning is there. So what is the basic applications of LangChain? So the LangChain, we can build like chatbots, we can build document analysis, we can do code analysis and generations, we can do creating contents, or like developing contents, or like education applications also we can make use of LangChain. So there are like several benefits of LangChain. So the easiest thing we can tell is like is reduced development effort. Because why? Because it reduces duplications work in it, and it avoids duplications, and it is easily like improved for scalability, and it has like enhanced efficiency feature in it, and also it's used for like a fostered innovations. So let's talk about the attacks on graph neural networks. So basically attack is means like a poison node which being used as a data, or as a input data, and then is being led into like a different set of target nodes in it. Once based on this poison node, and which being trained, and if there is no difference in that node, then it is directly attacked with the GNN, and it makes like a misclassification, and it changes the different way of predictions and everything. When you can see here as an example where like a node with a poison which is like being classified as incorrectly, but unlike here a node which is being used as like a poison, and it's being monitored by GN and guard, and it can predict correctly. That means like with the enable set of defense mechanism, we can prevent the attacks of graph neural network. So what is a backdoor attack basically? So backdoor attack is nothing but does like a malicious or like a Trojan is being embedded within a data, and it is like or embedded within a model, and later on it's being triggered automatically by that hacker, or by a user. So at the time, at the initial stages of like a data preparation and everything, we may not be aware of that. Why? Because it's being embedded within a model, or like different parameters, or like hyper chain tuning parameters has been made, and finally it's being like tuned in a way that it will release this triggers at a time of training, and make the predictions differently. So they are like two different types of backdoor attacks we have. They are like subgraph level attacks and node based attacks. So what is a subgraph level attack? So graph level attack means like there's like a new graph is being managed or added in a way to a main graph, so that the attacker or like the user um, designs in a very nice way, so that it is not being identified by the data preparator, or like by the algorithm at all. This is the one is like subgraph based backdoor attack. So node based backdoor attack is also like here. Here, the specific patterns is being included within the node and the edge features, which combines directly with the main graph. Here, the attacker designs in a way that there is no difference between what is a main graph and what is a subgraph level information. So all the graph level information makes it very similar, and there is no different way of understanding it. And that's how it's being targeted for an attack. So what are the examples of backdoor attacks? So one we can tell is like poisoning the training data. And like next is like embedding the trigger in the model parameters by changing the hyperparameter tuning and everything. By this, it makes the model to compromise and also reduce the model complexity. And it makes the model to have less awareness, like if that is being attack is being done or not. So that is the biggest thing here. So let's talk upon how we can go against these backdoor attacks and what is the different mechanism for this. So there are three different processes for defense mechanism is there. So one is that data sanitization is there, and data introspection is there, and certification is there. So let's talk about what is the data sanitization. So data sanitization means like we'll be cleaning the data completely and removing the potential malicious data points. So data introspection is like analyzing the model's behavior to identify the anomalies or patterns that could indicate the backdoor attack. And finally, the certification is like we're going to give like a formal certification to the model so that it is not being attacked by any users or anyone. So let's talk about some more in detail. So what all the different mechanisms is there? So one way of mechanism is like input validation. Means like involving verifying the input information of the graph we find to find like any patterns in the graph or like any triggers is embedded in there or not. And next is like model monitoring. So model monitoring is means like we'll be completely monitoring our model, finding what's the behavior of the model. Is there like any hyperparameter tuning is done explicitly by other than the developer or not, or like is there like any differences is there. So next is like adversarial training. Adversarial training involves the chain model of a data set, and basically here a trigger can be crafted inside the training stages. So now we have to find in a way that is there like any changes is being attacked or not. Now we'll be doing a complete mechanism of robust checking of each and everything, how the attack is being done or not, or like is there like anything way of sudden change in hyperparameters or not that not. We're going to have like small training mechanism here which going to detect that such a type of movements. So let's talk about like graph transformation technique. So graph transformation technique, it involves the input graph a training before feeding them to a GNN model. So it is done using a technique called like graph pruning, graph sanitization, and graph simplification. So let's talk about like ensemble learning. So ensemble learning is involves like combining multiple GNN models with different architectures or training parameters. So means he'll be having like a different GNN model. If one model is compromised, the other model will take over it. That's the basic of ensemble learning. So let's talk about like trusted computing environments. Here we will be deploying a GNN model in a trusted computing environments where it is safeguarded using a different hardwares aware devices which are available. So these hardware devices makes extra layer of protection and enables us to protect the entire system. So and finally, let's talk about like transparent and verifiable AI. So here it is being promoting like transparency and verifiable AI. By this, we can identify and address any potential backdoors at early stages. And this makes the model training and data architecture in a way which is being accessible by most of everyone, other not more not a common user, but to everyone of in a developer domain and everything, and they can scrutinize and evaluate these models. So let's talk about like impact of backdoor attacks. So impact of basic impact of backdoor attacks, they are like a mixed classification, and they are like a privacy leaks, and finally is like denial of service attacks. Let's talk about in detail about what is a misclassification. The misclassification means like the attacker can force a model to make incorrect predictions for graph containing the backdoor triggers. So directly leads to like a misclassification means like a mishap of a model. That means like model is completely compromised here. For example, if a model like let's consider example of a Tesla car. If consider if a Tesla car is being hijacked or like hacked by an attacker using like a malicious like a triggers which being like embedded in a training model. That means like instead of classifying the green signal, if it classify that as like a red signal, that means it automatically the car will be stopped in middle of a traffic. That causes the potential damage to for back cars or like completely mishap in a road. So it potentially like leads to like loss of lives and everything. And I'm aware that like the Tesla has like a very strong and high enabled security system for them. So this is the one example I just want to tell. So next is like is the privacy leaks. The privacy leaks means like the attacker can exploit the backdoor to extract the sensitive information from the training data or the input graph. Here, the input graph is like contains the heart. And why? Because it contains a lot of information about the users and everything. Say, for example, the user's preference, their likeness, their products, who is connected with whom, is a friend or like a wife or like a whatever is that. This is like basic information. If this data has been released out, that causes like a lot of mishap. So that's the important implication of this backdoor attack. And next is like a denial of service. So denial of service is also called like a backdoor attack, which makes the model to crash or completely perform very badly. That means like the level of accuracy is completely down. Say for example, a 99% to like 10% or something like that. That means like our entire prediction went into wrong. That's the denial of service attack. So let's have the question and answer session. And thank you very much for spending time in our 10 weeks journey of this course. And I have like a lot of questions I'm getting now. And let me answer them in a chat. So, so we have to, let's take off an example of yeah, that's very nice. Thank you very much, Dasleen, for your answers, questions. So that's the example. Like in a denial of service attack means like the model is completely crashed. So as I said, like let's take an example like one model which we have that is used to predict either the signal is like red or green or amber. So what the model crashing in a sense like it completely is down. That means like it's not able to predict what the signal is or what it is being connected or what how it's being modified to predict. That is the like concept here is being completely attacked. So since the model is completely attacked, it can't able to predict or it will be predicting completely badly. So here we need to have like a defense mechanism for that basically by like complete monitoring of training data and having proper checks with the training data, and we need to find if there's like any triggers has been embedded or not in the training data and also in the model as well. So by this we can counter the denial of service attacks. So yeah, thank you very much. So thank you very much for everyone. So today is our last session, and I'll be completely available in my official email ID. So any queries, please do revert me back. I'm happy to help you at any time. So thank you very much.